All right, so let's start getting into kind of the more important details here. So we've looked at theory. Theory is interesting because you can go either way with it, right? It's just an explanation. It could be completely full of holes, but it's some of the best explanation that we have. Now let's get into kind of the important vocabulary to understand here, which I'm told by my organic students, they hate vocabulary, but then some of them love vocabulary. So it's kind of a mixed bag here. But this is important vocabulary we got to learn. So it turns out when we take this methyl bromide and we actually react it with chloride, it says chloride, but it's just a hydroxide, a 5-member transition state forms that supports bimolecular substitution reaction mechanism. Let's look at the vocabulary first, then we're going to put this all together here. So here's our reaction that we've been studying here, and there's some important vocabulary to be aware of. So where are the reactants? Let's ask the class here. Where are the reactants in this? What side of the arrow are the reactants on, the left or the right? Left on this case, okay? Just making sure everybody's got a pulse in the room. Okay, where are my products? On the right, there we go. All right, so you passed the first test. We know people are alive out there. All right, good. Now, nucleophile. Great, great word. Think about the etymology of the word nucleophile, nucleus, right? Phile means what? Think about Philadelphia as being the city of what? Brotherly love. You don't know that? My goodness gracious, you need to get out of the Southeast. Nucleophile. Phile means love. That's the important point, right? So nucleus, what's a nucleus? It's what sort of a charge is a nucleus? Electrons are what? Negative or positive? Negative. So nuclei are what? Positive. So this literally means lover of positive charge. That's really what that is pretty much saying here, right? So if you're a lover of positive charge, what is that telling you about your nature? You must be what? What sort of charge must you be if you love positive charge? You must be negatively charged. So you want to take a guess on the reactant side where our nucleophile is? Which one is it? You have two choices. Yes, you do. The thing that's negatively charged. It's marked. You can't miss it. HO minus, the hydroxide is serving as our nucleophile, right? So it is electron rich. I'm going to go ahead and highlight that baby as being electron rich. Specifically, though, I'm going to highlight the oxygen because the oxygen's actually doing all the work in this case. Okay, electrophilic position. So let's think about this one. Oh, here you go. Phile again, right? So that means heart. What does electro mean? Nucleo meant positive. So what do you think electro means? Negative. So the thing that loves negative charge. And so if you love negative charge, that means you're inherently electron poor. So this is the part where you may not recognize this. The electrophilic position is the part that's kind of inherently negative or positively charged is the point here. And that happens to actually be the carbon that's right here. And so hopefully now you're starting to see where all of this is kind of coming together. The electron-rich red oxygen atom is attracted to, and this reaction is attracted to the electron-poor carbon atom in this case. But there's another creature that's still floating around in here, and that is the leaving group. You can tell this was developed by a chemist because it's very unimaginative here. But what does a leaving group actually mean? It's the thing that does what? Take a guess. Leaves. It goes away. So looking at this chemical reaction, what's going away in the reactants as they're converted into products? What went away? Br. This is your leaving group right here. That's exactly what this is. This is the thing that goes away. This is hallmark of what we call an SN2 reaction. These are the key characteristics of an SN2 reaction. That is, the nucleophile is attracted to the electrophilic position, and as it is, it ejects a what? It ejects a leaving group. That's the important point. That's the thing. It goes away. So what does the SN2 actually stand for? The S refers to, this is a substitution reaction. The 2 represents that it is a bimolecular reaction. That is, two things have to bump into each other in the transition state. We'll talk about the transition state here in a second. And then the n, the lowercase or the subscripted n, means that this is all initiated by what word started with n up here? Nucleophile. So this is a nucleophilic substitution reaction. It's a bimolecular nucleophilic substitution reaction, or we could just call it simply an SN2 reaction. And this is the reaction that gives students like the most heart palpitations, because they're like, oh my goodness, now we have to actually learn how these chemical reactions work. Well, guess what? You've learned a little bit about theory, so you actually know how these chemical reactions work. All right, so let's look at this whole transition state thing that's happening here. We know the nucleophilic position, the oxygen atom, is reacting with the electrophilic position, the carbon atom, and then Br is going away. So what's actually happening in this chemical reaction? Now, we also know something else too. Thermodynamically, we know that the reactants are very reactive. In other words, they have very high levels of reactivity. And since they're highly reactive, what does that tell us about their stability? Very low, low stability. So we generally define our reactants as being relatively, well, let's just say relatively high in energy. What about the products? It's the opposite, right? Because you don't want your products to react. You want them to be stable. So what's happening for the products? We have low reactivity. And then we have high stability. And this tells us something about the energy. The overall energy is fairly low for the products. So this is going to be vitally important to understand what's happening. All right, so let's put this all together. Here's our chemical reaction. We're going to draw out what's called the reaction coordinate diagram. This is provided for you in your notes. We're plotting the energy of the system as a function of the coordinate. And you go, what is a reaction coordinate? Details. That's what this is. This is telling you how the reactants are turned into the products is the key. All right, so we start with our reactants, and we said that the reactants compared to the products are a little higher in energy. So what are we going to say here? We might say, maybe start like right about here. This may represent the total energy of your reactants right here. That's at the start of the chemical reaction. See how it's kind of closer to the left side of that arrow? That's the beginning of your chemical reaction. What about your products? We said they were lower in energy. So where do I want to put the product line? To the right, obviously, but do I want it above the R or below? Below the R right here, right? So this line represents the total amount of energy of your products. All right, here's where the magic happens. As I take hydroxide and I start to push it in to this carbon that's right here. Remember, we'll put the color scheme in. As I take this oxygen atom and it goes into the carbon atom right there, remember, the carbon atom is surrounded by electron density. Oxygen is inherently negative. So when I take two negatively charged things and I start to bring them together, even their electron clouds, what's going to happen to their energy initially? As I take two electron clouds that are both negatively charged and I bring them together for the sake of forming a bond, they get closer and closer and closer. They start to feel each other. They're both negatively charged. Repulsion takes over. So what does that mean for the energy? It goes up, way, way up in this case. So what happens to it? This is literally what's happening. I had a professor in college that used to say this a lot. He used to say, as I bring the reactants together and the reaction proceeds forward, we start to see an increase in the energy until we get to a certain point where the energy maximizes. And that is where the reaction can go in either direction. This is referred to as, some of you guys are going to love this, this is called the transition state. We symbolize it with a TS. There you go. Swifties in the house. And then once you get to the TS, it's interesting here. The reaction can either go forward towards the products or it can go backwards towards the reactants. So this is why it's a transition state. The reaction can go in either direction is the key here. So the question really becomes, what does the transition state look like here? How is this thing actually forming? What's actually happening here? Well, let's sort of see what's happening. I need to take my hydroxide. I got to bring it in closer and closer and closer and closer to the carbon. And then what ends up happening? When you get to the transition state, you have a hydroxide that hasn't formed a complete bond. It's a partial bond with the carbon atom. And what's sort of fascinating about it is that the carbon atom, instead of it kind of taking on this sp3 looking shape to it, it sort of flattens out, changes its hybridization sort of. And of course, carbon doesn't like that at all. But what's interesting is that you also have sort of broken a bond between the carbon and the bromine in this case. This whole thing, we never isolated, by the way. You can't isolate a transition state. But this is what our transition state looks like. Now, we symbolize transition state with a double dagger like this. And we're going to also put a little negative charge in here to indicate that you actually have negative charge throughout the system. And you go, well, where is that negative charge coming from? Well, it turns out in this case, you have partial negative charge that's on the oxygen. You have partial negative charge that's on the bromine. But then that's all balanced out with a little bit of partial positive charge that's actually on the carbon right here. But the bottom line is that you make this transition state. It is a very high energy species. And this is the transition state that you're going to see for an SN2 reaction. That's it. You can't see any other type of a transition state. If you know the reaction is proceeding via SN2, you can basically predict what the transition state is going to look like.